Welcome to Study Loop.
So in this problem, we are given a process over an ideal gas that is involving actually two sub-processes. This is from A to B and from B to C. Now, from the figure given, we can see that the starting process, AB, the first process, is the process where the pressure increases while the volume is constant. And the lowest temperature is the initial one, the one that is corresponding to this part of the process. Since we can see that from the figure, therefore, we can evaluate the lowest temperature from the ideal gas equation, which goes as follows. Pressure times volume equals nRT. And this T will be the lowest T. For the first part of the problem, we need to evaluate it. So let's rearrange the equation to evaluate the T. So T will be equal to P dot V over nR. And here we can simply substitute the known values. So this is going to be 0.2 times 1.013 times 10 to the fifth. This is in pascals, so we're transforming from atmospheres to pascals for the pressure, and here we will have 2 times 10 to the minus third. This is for the meters squared, and down there we will have 0.0175 times 8.314. And the dimensions of this are going to be in Kelvin. So when all dimensions are together put, they turn to temperature, to the elementary unit for temperature. So when we put these values into a calculator, we obtain that the final answer is, for the part A, is that T equals 278 kelvins. Now this is for the part A. For the part B, here we need to find the work done. Now, if you observe the first part of the process from A to B, we can see that the work done must be zero because there is no volume change. When from the definition of the work, we know that work is an integral from V1 to V2. Pressure is a function of volume, differential of the volume. So if V1 equals V2, then the whole integral will be zero. So by definition, in such cases, the work done will be zero. And therefore, work from A to B will be equal to zero. Now, we should find the work from B to C. And if we observe the part of the process from B to C, we can see that there is an increase in volume from 2 liters to 6 liters. So we can say that this part of the process is a half of the loop process. If we say that we have a loop process from A to B to C back to A, and we know that for any loop process, this is from the theory, the work done can be evaluated as P1, P2, V2 minus V1. Then, for 1/2 of the loop, which is work for BC, it will be 1/2 of P1 plus P2, V2 minus V1. Why? Well, this is because this is just 1/2 of the thermodynamical state loop that we're observing here. And we need to substitute the known values here. So this is going to be equal to 1/2 over 0.3 plus 0.5 times 1013 times 10 to the fifth. This is pascals, and all of this times 6 minus 2 times 10 to the minus 3. This is meters cubed, from liters to meters cubed. So the total dimensions will be in joules, and when you put these values into a calculator, we obtain that the work BC will be equal to 162 joules. This is the final answer for the part B. And for the part C, we need to find the internal energy. Now, internal energy is, from the first law of thermodynamics, the total heat of the system, Q, is always equal to the internal energy change plus the work done. So then we can say that the internal energy will be equal to Q minus the work done. And we know the work done, since we evaluated it, it is only equal to the work from B to C. That is the total work done, since work from A to B is 0. So we can simply substitute 162 joules there, and we know that the heat added to the system is 215 joules. So it will be 215 joules minus 162 joules. And simply subtracting these numbers, we obtain that the total change in internal energy will be equal to 53 joules. Now, all parts of the problems are solved, and I hope this was helpful, and I hope to see you in the next lesson. Bye.